Good afternoon, everyone. My name is Alice. Welcome to the webinar organized by PolyU CEE and HKIE Civil Division. Today we have our guest speaker, Dr. Zhuang. Dr. Zhuang is a research assistant professor in civil and environmental engineering at PolyU. He specialized in aerobic biotechnologies for wastewater treatment and biomass valorization. His work focusing on improving energy recovery from sewage treatment and producing valuable chemical from waste streams. He also developed strategy for mixed cultural fermentation and reactor design to enable sustainable waste conversions. Today's presentation will explore elongation as an innovative aerobic biotechnologies for converting food waste into valuable medium-chain carboxylate ACE. The elongation biotechnologies could redirect carbon and electrons flows to generate higher value liquid products, supporting circular bioeconomics goals. Dr. Zhang's study presents an integrated process that combines enzyme hydrolysis carbon um, with carbon chain elongation, sorry, um, to convert food waste into N-carboate. The process combines enzyme treatment to break down food waste and aerobic reactors that produce N-carboate efficiently. The approach could transfer food waste into valuable products, supporting sustainability and the circular economics. After Dr. Zhang's presentation, we will have Q&A section at the end. So if any of you have questions, you can type in the chat box. So without further ado, let's welcome Dr. Zhang.
Thank you for your introduction. So before this in front of this webinar, I will first introduce our department. So I come from the Department of Civil and Environmental Engineering in PolyU. So as we all know, our department actually is quite strong in the civil engineering and environmental science and also in the transportation science and technology. So in recent ranking, for example, the Shanghai ranker ranking, we have the top number one in Hong Kong for the civil engineering and transportation science and technology. And also we rank in 44 in environmental science and engineering in the world. And also we have a quite nice QS ranking for our department, especially in civil and structural engineering. And also we have very high rank in the US ranking. So we have a strong team for our research. So we have 29 CE scholars ranked for top two scientists. And we also have uh, nine academics and the Changjiang scholar of China. And we achieved recent year, we achieved theme-based research scheme. We achieved four. We also secure a lot of external funding source, especially the IIF and Green Tech Fund, and also RCC Cooperation Research Fund, CRF. And we also very good at our academic program, including the undergraduate program, top post graduate program, and also research postgraduate program. Okay, so we have many outstanding alumni all over the world and Hong Kong. Okay, so if you are interested In us, you can follow us our social media shown in the screen. So now we can start our topic about the food-related waste stream valorization for Caproate production via carboxylate chain elongation. Okay, let me introduce myself again. So my name is Huichuan Zhuang. I'm a research assistant professor in the Department of Civil and Environmental Engineering at the Hong Kong Polytechnic University. So my work actually sits at the intersection of wastewater treatment, food waste valorization, and environmental biotechnology. So today's topics really come from our lab and our team. So the title is about the food waste stream valorization. So first of all, I will talk about the food waste problem in Hong Kong. So, like many dense cities, Hong Kong generates a large amount of food waste every day from household, restaurant, and the catering sector. So, as you can see from this figure, so actually Hong Kong people produce the most uh, amount of organic waste all over the East Asia. So you can see Hong Kong, the bar of Hong Kong actually is higher than Japan, South Korea, or also China. So in terms of strategy, often talk about four keywords from our government, which you can also see like reduction means simply avoiding food waste in the first place. And donation means redirecting those edible surplus to people in need. And also collection and recycling means we do some separation collection of food waste. And then uh, we in Hong Kong especially we use the anaerobic digestion system for treating those collected food waste. However, nowadays we have OPAC 1 and OPAC 2, and also we have some co-digestion system in starting with sewage treatment works. However, the overall treatment capacity of those food waste is 500 tons uh, of food waste every day. So this number actually is um, far away from the total food waste generated every day. So we still have some substantial about amount of food waste going into landfill actually. So I will discuss in a moment. In Hong Kong, the municipal solid waste charging scheme was originally designed to be a key driver for waste reduction and separation. Okay, the basic idea was quite simple. If we pay by weight or by bag or mixed waste, we will have a stronger incentive to reduce it and separate uh, recyclables. But however, as you know, this charging scheme it has now been proposed. Uh, we don't have a short time, so at the moment we don't see a direct price signal at the household level. However, the behavior logic behind this scheme is very important for us for two reasons. Similar charging mechanism may appear in the future in Hong Kong, and other many other cities already have pay as you throw system like Taiwan and like the cities in Japan. So they still have same question about waste and so under such scheme, one particular device has become very attractive to citizens. So this is the food waste disposal you can see in the picture. So or we call it food FWD. It allows people to grind food waste in the kitchen sink and flush them into the sewer. So the from uh, user point of view is extremely convenient. No smell and very fast, and no storage of those wet food waste, and you don't need to take it to some facility to to treat it. But if a charging scheme is in place, so people might just simply want to purchase those equipment in their house. So we do some study on the Google trend. So we compare some keyword at those uh, when we are going to when we was trying to do a charging scheme. Okay, so we compare two keyword. One is for the waste charging, another was food waste disposal. Okay, so we found that when we the charging scheme is going to apply, okay, in like 1 years ago, people start to search the keyword food waste disposal. Okay, so we believe that if the charging scheme is applied, so part of the food waste will directly discharge into the sewer. Um, so we want to answer a question that what we if that happens, so what is the affection for the sewage treatment plant and also the uh, carbon emission or the energy consumption of that action. So here's our first study about the food waste and the wastewater treatment system. So wastewater treatment system are often the large single electricity consumer in a city environmental infrastructure. Okay, so with the typical trend, aeration will be of the activities large process will consume a lot of electricity. So here we saw the water treatment process is very important, and we create 5 different scenarios in, in order to estimate the impact of the sewage treatment system affected by the discharging food waste through the FWD. So we create 5 scenarios. The first scenario in the light blue is the food WD with AD. So in this scenario, the food waste is collected by the sewer, and then finally, after wastewater treatment process, the sludge is treated by anaerobic digestion, and finally it comes to the landfill for the digestion. The second one actually is quite similar to the first one. However, the difference is the sludge produced by the wastewater treatment system is treated by the incineration. And then we have the uh, yellow round. This is the separation system with the AD anaerobic digestion. In this system, we don't use any wastewater treatment facility to treat this food waste. Okay, it just collect, collected, separated, collect, and transported to aerobic digestion facility like OPAC 1. Okay, and the pink broad is about the food waste collect, separated collect, and then transport to the incineration plant for energy generation. And the final one actually is the current situation of food waste, most of food waste. The the dark blue road is about the food waste is connection with the municipal waste. And finally, it direct go to the landfill. Okay, so our assumption is that if we uh, allow people to use the food waste disposal in their home, about 50% of household food waste finally go to the sewer. So what happened? To estimate that situation, we select 3 different wastewater treatment plants. The first one is starting with sewage treatment works. It is to to represent sewage treatment works controlled with controlled aeration and for the nitrogen denaturation and nit nitrogen removal system. However, this system actually is no food waste inside. And the second one is renal sewage treatment works, which is represent a sewage treatment system that it it don't need to remove nitrogen. So only over aeration condition was applied, and also no food waste is inside in the infrared. So this means we just try with the high field condition in this aeration tank. Okay, the third wastewater treatment system is in Los Angeles in United States. As you know, this uh, American people actually use the waste disposal. So they are you can see from this table the BOD, COD, and also the nitrogen ammonia nitrogen is actually is quite high compared to those two plants in Hong Kong. So this is the ammonia system actually is represent the wastewater treatment system, which is control uh, aeration with the target of nitrogen removal. So for estimate the aeration efficiency uh, challenge of food waste introduced, so we we do some field study about the off-gas test to test the different aeration efficiency. So you can see in this picture, we create a hood to collect the off-gas of the aeration. So by comparing the oxygen concentration in the off-gas and also the different parameter, finally get we can simulate and we can estimate the aeration efficiency and in different sewage treatment plant. So here is some result of this test. So you can see from the left-hand side is the basic aeration uh, system, aeration efficiency about the sewage treatment works. So we can find that uh, with actually the food waste in the sewage affect a lot. So you can see the different alpha SOTE uh, is shown for different sewage waste without food waste. And also the process design for example, the nitrification and denitrification also affect a lot. So you can see there is two different line in the alpha SOTE uh, figure in with it with the denitrification and without denitrification. So we summarize those simulation results and we created an energy profile and also the greenhouse gas emission profile in the right hand side. So you can see with food waste and without food waste actually it's quite different for the energy consumption and also the uh, greenhouse gas emission. So around 30 to 40% uh, of the energy consumption will be increased according due to the added food waste into the seaweed. Okay, and also the same happen in the greenhouse gas emission. So for this route, we found that actually uh, the food waste disposed to sewer actually affect a lot to the sewage treatment plant. So what happened? if we just separate those food waste and put it in somewhere else, for example, the AD fermentation or also the incineration plant. Okay, so this is the result of that. We compare the different greenhouse gas emission and the cost, also the operation cost, because cost actually is very important parameter to decide which uh, system our government will choose. Okay, so we found that current situation, we directly put those food waste into the landfill, will cause a very high greenhouse gas emission. However, if we use the food waste disposal, okay, we discharge about half food waste into the sewer. Uh, the carbon emission also very high, but uh, lower than the landfill weight, but also very high. And however, it also causes a very high cost of the operation of the wastewater treatment process. But you can see that if we separate those food waste from the municipal waste and we do some aerobic digestion, for example, the emission will be very low, okay, compared to uh, the, the landfill or the food waste disposal method. Okay, very low emission. And also, it can create some revenue benefit. Okay, the cost is negative means it earn money. So money actually can push us to choose that uh, process. That is very important. However, for the anaerobic digestion, actually the methane is the final product. But actually, methane, the price is not as high as other chemical, high valuable chemical. So then we propose a food waste valorization uh, process to treat those separated food waste. Okay, so this is our second study. So we propose to use some enzymatic hydrolysis first to rapidly convert the food waste into three parts: the crude oil, liquid hydroxide, and also solid residue. For the crude oil, we can convert those oil further into the biodiesel. Okay, biodiesel you can make it into like uh, environmental friendly fuel, and then the solid residue can be converted by the composting process, and we can make some organic fertilizer, which also benefit to our society and our environment. But how to treat those liquid hydrogen? So we have we propose this bio, biological process, carboxylate chain elongation process, CCE. So the product of this uh, CCE process actually is caprate, this six carbon chemical. So the caprate has very interesting characteristics compared to other fermentation products like ethanol. Okay, so caprate is the solubility is very low, around 10 gram per liter. So that means it's very easy to extract from the mixed liquor. And then the pKa is also low, so it can be the self-buffering during the biological fermentation process. And it also is a high energy content chemical, so it can be the precursor of biofuel or also like bioplastic. So here we propose a two-step fermentation. So first step, we use the enzymatic hydrolysis to convert the food waste into glucose. Okay, and in the fermentation process, so you can see from the left-hand side, during the acidogenesis, the ethanol and short-chain fatty acid and also lactate will be produced in the fermentation system. Then in the elongation process, the core reaction is the reverse beta oxidation. The short-chain fatty acid will be converted into the medium-chain fatty acid. Okay, so we did a optimization process, a study for the food waste enzymatic hydrolysis. So you can see we for estimate the uh, correct the response of the enzymatic hydrolysis. We choose the some different uh, food material with different cooking and or pretreatment method to uh, get uh, the experiment result to simulate the real situation. So the left-hand side is our experiment material. Okay, it's some common food in our restaurant. We use the kale leaves and the kale stem to uh, represent the uh, different form of the cellulose or negative cellulosic material in our food. Okay, we also try different cooking way. We use the steam cook, and also we fry those material. And then we use different pretreatment method uh, to test those different food. Okay, because in our enzymatic hydrolysis, sometimes the enzyme will be inhibited by different components in the food waste. For example, the starch during starch hydrolysis, even some amylase. Okay, the lipid will inhibit the amylase uh, hydrolysis. So here we also do some mechanism study about those enzymatic hydrolysis. Okay, so this is the result of the enzymatic hydrolysis optimization. So we found that actually the different cooking method affect our enzymatic uh, hydrolysis efficiency. Okay, the substrate enzyme digestibility is affected by different uh, cooking method, also the pretreated method. And however, we find some optimized enzyme dosage for all different food. Okay, we found that 0.5% of glucose amylase actually is good for starchy food waste, and 3% of CTAC2, which is cellulase, is good for lignocellulosic food waste. And if under this condition, we can convert around over 90% of food waste into sugar, lipid, and also amino acid. So after enzymatic hydrolysis, our system turned into the Caproate fermentation. So it's the elongation process. So in our lab, we built a 2-liter fermentation system. So in like 25 days, okay, in this system, our Caproate concentration reached to 22 gram per liter, with the glucose conversion rate around 50 to 60%. Actually, uh, this productivity is already higher than the methanogenesis and aerobic digestion, which means we can obtain more valuable chemicals from those this kind of food waste. And also we do some uh, bioinformatics study in this system. Okay, so we found that Clostridium curvivore, okay, which was response for the external train elongation, external driver train elongation, which convert ethanol to acetyl-CoA and also perform the reverse beta oxidation pathway, then produce the caproate as the final product. And also we find some protein classicums and one unclassified bacillus facilitate with the ethanol oxidation, which is some uh, competing uh, reaction in our system. Okay, and then we find some uh, sporon anaerobic factor, which represent homoacetogenesis, facilitated with the Wood-Londa pathway. So this pathway can convert the carbon dioxide into formate, and then it can further convert into acetyl-CoA. So this product can be go into our reverse beta oxidation pathway. So this means this bacteria also help to improve our conversion efficiency in this system to utilize all the electron and the carbon. Okay, so the microbial synergy interplayer promote the overall Caproate carbon conversion rate that is uh, which make the fermentation result reach our target. So here we found that the ethanol actually is the typical chain location electron donor with no redox potential and low energy content. So like the right hand side, you can see the redox potential and gives free energy for this different reaction. We also find the uh, hydrogen carbon dioxide driven chain location is highly energetic, and actually it doesn't support the chain location as the soil substrate without external energy supplement. However, in this with the synergetic interaction among different bacteria, okay, this reaction can improve uh, the energy and the electron utilization rate. Okay, so in conclusion, uh, we found that sewer and landfill disposal of food waste pose very high, very large, heightened greenhouse gas emission, okay, and energy burden of a city. So the source separation plus AD anaerobic digestion or fermentation could reduce this net greenhouse gas emission, and can even yield some revenue benefit. And by applying the enzymatic hydrolysis, we can convert the food waste into a stable fermentable uh, hydrolysis, which means it has a lot of sugar or very variable usable nutrient for following fermentation. Okay, and capsulate elongation and upgrade those hydrolysis into an encapsulate. So this is a high value chemicals. So it can help uh, our society willing to treat those unwanted food waste. Okay, in the end, thanks to our um, group members, especially our PhD student Guan Jianyu and Yang Shihui. So they put a lot of effort in those studies. And also thanks our team. Okay, so that's all. And also thanks the HKIE to provide this a platform for sharing our study and our story.
Oh, thanks, Dr. Zhang. If anyone have questions, you can type in the chat box. We have our first question. So someone asked, after source separation, where should be the enzymatic hydraulics can be taking place with large quantities of food waste collected in Hong Kong?
Sorry, could you repeat the question?
Um, yes. So after source separation, where should be the enzymatic hydrolysis be taking place with large quantity of food waste which collected in Hong Kong?
Okay, so compared to the current system like OPAC 1 and OPAC 2,
Mm,
actually they use like the SRT of their system is like 20 day to 30 day. For enzymatic hydrolysis system, it only need 12 to 24 hours to finish whole procedure. So
mhm,
actually we can save like we only need 5% of the space compared to those anaerobic digestion process. So that mean we can collect 20 times more than the AD process here.
mm,
Yeah. So I think it's possible to do the automatic hydrolysis system in Hong Kong.
mm. Uh, yes. So um they someone asked before going to AD, what pre-treatments could be done to be improve the performance?
Before going to AD, you mean the hydrolysis, right? So actually, we uh, after hydrolysis, you can see we have three parts of product. First is the crude oil, and second is the hydrolysis, liquid hydrolysis, and third one is the solid residue. So uh, better separation actually is good for the AD process. Oh, sorry, if you ask me about the AD, I think for food waste, the biggest problem for AD actually is 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 sometimes it causes the acidification of the AD process. So maybe the pretreatment uh, now for those systems actually is co-digested. So it may need to mix some, for example, like sewage sludge to slow down the acidification uh, process. Means it can stop the pH drop during the AD process. Yeah, because nowadays the actually if the anaerobic digestion for food waste, the biggest problem is that the pH will drop very fast in a short time. Yeah.
Okay. Um, so did you carry out any pilot scheme with the government to treat the food waste by using the proposed method?
Pilot scale. No yet, not yet, because we just do some lab scale study to figure out to estimate, okay, to estimate the performance of this system. Yes. But in the future, we may try to apply some like pilot scale system and cooperate it with the, for example, OPAC one.
Mhm. Mm, I see. Mm. Any more questions? Okay, so thanks again for Dr. Zhang. If anyone got questions, I think you can email Dr. Zhang directly with the email below. So thanks again for everyone attending the webinar today, and I think that's the end of today's section. Thank you all, and looking forward to see you in the next one. Thank you.
Thank you. Thank you.